first component is the fingerprint representation. It's a compact, discriminative, and needs to be efficient. And this efficiency is like to compare two fingerprints to check if they are similar. And together with the representation, we have the structure. The structure is a way to organize the data in a way that allows for fast retrieval. So using a data structure that you can prune the center space to find the most similar elements given a query. So a couple of examples is the minutia triplet with hashing, the minutia cylinder code with locality sensitive hashing, and deep read with a project compilation. So what is our proposal? We have a focus on the index instruction itself. So while most research focuses on crafting better representations, our work explores a flexible, non-metric, and representations agnostic indexing structure. So we relax the couple between the representation and the structure, and here we are looking for an indexing structure that can support multiple representations. So how do we proceed with this? We consider firstly the cursor dimensionality, so the problem of searching high-dimensional vectors, and with this in mind, we turn to approximate nearest neighbor search techniques, focusing on proximity graphs. These search and proximity graphs have their roots in the lonely graphs. They are the dual part with the Voronoi diagrams. So specifically in this case, we focus on HNSW, which has been shown to achieve state-of-the-art performance in various applications. And here is what is HNSW. It stands for Hierarchical Navigatable Small Worlds. This structure is a layered proximity graph that works by the search and insertion work by a greedy top-down parse to find traversal. So the search begins in the sparse upper layers with long-range links and moves to denser lower layers with short-range links. The top layer contains the fewest nodes, while the bottom layer contains all of them. So here's this figure shows an example of the workings of HNSW. We start at the blue arrow, and we traverse, do a greedy traversal for the first layer until we reach the nearest node to the target. When we find this local optima, we repeat the process by going the layer down with some short range links and a finer grained search. And we repeat until the bottom layer. So to test this approach, we have an experimental setup with a query containing 2,800 impressions from the public FBC benchmarks, a gallery that is approximately 400,000 fingerprints from both public and in-house database, and we use as a baseline the one-to-end search, that is video exhaustive search. And we have three representations that we're going to test. The first one is the global feature, that is a convolutional network based extracted from the whole fingerprint image. The second representation is based on local minutia descriptors, so we extract a patch from minutias, and we use another convolutional network to extract embeddings. And the last one, we use a black box. So we have a commercial off-the-shelf software that has both an extractor and a matcher. Matcher to give us a measure of similarity. So we are going to test even this black box to check if this approach works for non-metric arbitrary similarity functions. And here is our first result using the global feature vectors. Here we achieve nearly 30 times speed up. That is equivalent if in this systems, an APHIS, we had a workload of 1 hour, we could reduce it to 2 minutes. So, and we have a minimal accuracy trade-off, only 0.0 percentage point drop at rank 1. So here's the table of the results, 30 times with just 0.0 percentage points drop at rank 1. And we have orders of magnitude difference in the number of distance calculations. Here is the CMC curve, and we see that along all the ranks, the cumulative recognition stays very close to the brute force approach while giving 30 times more speed. Here are the second representation. We can, the minutia-based descriptors. So here, for each fingerprint, we have more than one embedding, so the index is larger, but this approach is better suited for bigger indexes because we have a logarithmic scaling for the search process. So here we have 170 times the speed. So we reduce a load of 5 days to just 40 minutes with no accuracy gap in rank 1 in this specific case. So we have about the same result. And this is more interesting because the rank 1 accuracy here is larger when compared to the first representation, because here we have rotation invariant and local characteristics that are redundant. So it's so fast based and much better in accuracy based on the previous approach. And here are the last case, the commercial off-the-shelf templates. So here we don't have access to the methods, but even still we can achieve a speed of 23 times. So here the key metric is the reduced expensive code smashing operations. We cut the total code smashing falls by nearly 90%. So what we can achieve with this? We can accelerate legacy pipelines without touching the proprietary comparator. And we have only a 1.18 percentage point drop in rank 1 accuracy. We have a flat line here because at rank 1, the software actually achieves 100% accuracy. And here are the failure cases. We check a predominant pattern, that is the low overlap between the query and the gallery images. So the graph may converge to local optima during the search. So conclusion, HNSW is a versatile and powerful accelerator for fingerprint identification systems. We can gain a lot of speed without needing to re-engineer the whole system. So it has a unique ability to handle non-magic commercial off-the-shelves that we can use as a black box. And in future work, we may optimize the index structure, so manually adapted tuning of the parameters, and we can design new representations tailored for this representation and extend the methodology to other biometrics like face and iris. And this is the acknowledgements. Thank you. Okay.
Do you have any explanation for the mistakes made by your system? The material process. Yes.
This one? Yes. Actually, because of the low overlap between the fingerprints, the search process that is actually searched in the graph, they converge to a local optima. So they are comparing this low overlap regions with other fingerprints that they are mistaken to. So they converge to a imposter. Like they needed more information to converge to the global optima. And well, the graph has inherent trade-offs because the graph algorithm is not exact. It trades a small accuracy for speeds.
Any further questions? So thank you very
Thank you
much.
so much.
Next presentation is the working titled Has UNet a lightweight residual UNet for scalable fingerprint enhancement?